Okay, so we saw how sensitive the EOQ was to changes in Q, changes in D, the cost per item, the cost per transaction order, all the different input variables, and we found it was very robust. It was very insensitive. The thing that we didn't look at yet was time. So let's take a look at that, because that's kind of a special case. So the question is, why is it different? Well, because the time is when we're going to have to do something, right? So you want to make sure it's practical. That's a critical thing with everything we do with inventory theory or anything with supply chain. It's more important to come up with something that actually gets executed than something that might be theoretically optimal. We want to make sure that we can actually implement it. So for T, we want to make sure the time is something practical. In our previous example, we found that the order cycle time is 73 days. So it'd be very hard to expect someone to every 73 days to place an order for something. So what you want to do is come up with something that's a little more practical, a little more reasonable. Also, this has the added benefit of being able to aggregate things. Because remember, everything we've looked at is one item at a time, but if I have multiple items, maybe I want to aggregate them to common order schedules. And so this is another way to do that. And so looking at the previous example, these numbers should be very familiar to you at this point. Right? The Q star is 400 units. We found our total relevant cost of $5,000 per year. And we found our T star to be 0.2 years, 73 days, or 10.4 weeks, nothing of which is very practical. Based on the equations that we developed before, I can really find quite simply what the change in the total relevant cost will be if I pick a different T compared to the optimal T. I give you two examples here. If I do things weekly and then monthly, and all I'm doing here is substituting in, knowing that T star is just equal to Q star over D. And so therefore Q star equals D times T star, right? I just carry it through, plug it in, and it's the Q over Q star, and the D's cancel out. So it's pretty straightforward. You could figure these out. You can check my math. But we want to do something a little bit different. And what we want to do here is use something called the power of two policies. This is a very clever heuristic, and essentially what we're going to do, we're going to pick a base time period, whether it's a day, a week, or a month, and I'm only going to order in powers of 2 of that. And so powers of 2, 2 to the 0th, 2 to the 1st, 2 to the 2nd of whether it's a day, a week, or a month. The nice thing about this, it sounds a little strange, but it guarantees that the total relevant cost will be within 6% of optimal. That's pretty amazing. So let's spend a little more time and get into details of how this works. So essentially what you're going to do is whatever your T star is, I'm going to pick a K so that that T star falls between 2 to the kth and 2 to the k plus 1. So here I have 2 to the 0th. That's if my base period is a week, right? So I'm saying a base period is 1 week. Then this 2 to the 0th would mean I'm ordering once a week. 2 to the 1st means I'm ordering every 2 weeks, 2 to the 2nd every 4 weeks, every 8 weeks, every 16 weeks, and so on. And so I want to pick the T star, I want to pick the K where my T star falls in between those. So in the example that we did before, where our T star was 10.4 weeks, we would pick where K equals 3, right? Because it falls within that. And so is it optimal? No. But it's within 6%. So let me go through and explain why this is so, because it's really interesting to be able to understand how this works. So here's my time, and suppose I've got, so these are all 2 to the k's, and suppose my k is based off a week. So my base time is a week, and I know that this could be a t, and let's say k is equal to, just for the example here, k is equal to 3, right? So this would mean this would be every 8 weeks, and this would be 2 to the k plus 1, 3 plus 1, or to the 4th, or 16 weeks, which is the same thing as 2t, right? 8 and 16, it's just 2t. And so the question is, let's say T star falls somewhere within this time period. Where's the worst possible case where it could fall? And you'd guess, if you think about it a little bit, the worst possible case is if it falls right in the middle, where T star is right there. And the middle would be defined as where the error from this side, coming from the T, is equal to the error coming from this side. So the point where those two are equal to each other is the worst possible error. Because if t star is close to this t, or close to this 2t, then going to there would be even less. So the worst possible case is where those errors are equal to each other. Now what's interesting and important to realize that the point where those errors are the same is not the middle between 8 and 16. Because 8 and 16, the average of that would be 12, right? So the middle there would be 12. When in fact, for those errors to be equal to each other, what we'll see is that it's actually where 2 is to the k plus a half. In this case, 2 to the 3.5, which if you calculate this through really quickly, comes out to be 11.3. So it's not that it's in between the t and the 2t, it's where the errors are the same. So how are we going to figure this out? Well, the best way to do this is to set up our equations. Let me just erase this stuff, make it a little easier to see. So what I'm doing is I'm setting the error from the left, that's this, right? The t over the optimal t and the t over the t optimal over the t here. And then this is the error from the right. And again, this 2t over the optimal t and then the t star over 2t. So where these two errors are the same, that's the worst possible case. So where is that? Well, all I'm going to do is set these equal to each other and cancel out the halves. Going to bring all the terms with a t star onto the right and everything with a t on the bottom to the left, and just use some simple algebra, clean it up until I get these relationships. The t over t star is equal to the square root of 1/2, and take the inverse of that, and obviously t star over t is going to be equal to the square root of 2. So now I'm going to take those terms and just plug it right back into our equation that we had for finding any kind of sensitivity for EOQ. And you see it comes out to be 1/2 times 1 over the square root of 2 plus square root of 2 over 1, and that turns out to be 6%. Amazing, isn't it? So the idea here is if I pick power of 2 intervals, it's guaranteed to be within 6% of the total relevant cost compared to the optimal interval. So the process you do to use this in practice is very straightforward. Find the t star. Find that optimally from EOQ. Pick your base time period, a day, a week, or whatever it's going to be, and then you find the lowest value of k that satisfies that. And so you know the t star, you do t star divided by square root of 2, and square root of 2 times t star, and you find 2 to the k times your base time period, whether it's a day or a week or a month, that falls between those. And then that's what you use, and you're guaranteed to stay within 6% of the ratio of the relevant costs. So let's do an example, because it seems complicated, but to use it is actually quite simple. So here's a different example. I know you're getting bored with the one I've been using. So my demand is now 25,000 units per year. My cost for placing an order is $750 an order. You see the cost of the product is a little lower than it was before, $25.50, and my holding cost is 15% per year. So what I want you to do is figure out Q star, figure out T star, and figure out what your total relevant cost is. Okay, pause the video, figure these out, and when you're ready and you've got numbers, then start it again. Okay, I've assumed that you've actually done the calculation, so let me just show you what I came up with. And if your numbers don't match these, pause the video, go back and try again. Try to figure these out. This is straight EOQ, and you should be able to get these numbers. What I really want to do is answer this question. Suppose I don't want to order things every 0.125 years. I want to find something a little more reasonable. What should I do? Well, let's go and say, okay, my base period is going to be a week, because I order things generally on a weekly basis. So what is my T star going to be? Well, my T star is going to be equal to 52, because there's 52 weeks in the year, times 0.125. And that comes out to be 6.5 weeks per order. There we go. So what I want to do now is I want to find the bounds for that. And so remember we said I wanted to find T star over square root of 2. And what is that equal to? That's equal to 4.6. You can check my math. 6.5 over the square root of 2, which is 1.414, because it's 4.6. And then I want to find the ratio of t star times square root of 2. And what's that equal to? That's equal to 9.2. So I want to find some term of 2 to the k that falls between those. So I know 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. 8 falls between that. So I'm going to use 8, which means my k is equal to 3. So what does this mean? I'm going to order 8 times per year. So that's going to be the same thing as equal to 0.1538 years per order, right? I just multiplied by 52. 8 over 52 will give you this. And so what will my order quantity be? Because if I'm ordering that frequently, my Q is going to change. Remember, Q is just T times D. So my T, we just figured out, is 0.1538. And I'll multiply this by my demand, which is 25,000. And for this, I get my new Q is going to be equal to 3,846. Okay, so that's what my new Q is going to be. But let's make sure we're doing things correctly. So let's find out what our real error is. So I want to go and look at what my total relevant cost from the T that I picked and compare that to the total relevant cost for what the optimal T is, right? And this is just going to be, 1/2 times 8 over 6.5 plus 6.5 over 8, because remember I decided to do it every 8 weeks and the T star was every 6.5 weeks. And if you crunch this out, it comes to about 2%. But let's say I don't trust the formula. Let's just figure it out long way, right? TRC for the total relevant cost for the T is going to be equal to what? Well, I've got my order cost, $750 per order, times 25,000 is my demand. And my Q, we said, was 3,846. And I'm going to add in my inventory holding cost, which is 25.5 times 15%. That's my C times my H, times my Q, 3,846, divided by 2, because it's the average inventory on hand. This comes out to be 12230. All right, so now we already figured out, so this is my total relevant cost for T. We already figured out that total relevant cost for T star, remember you did this earlier, was 11976. So if I just divide those two, this will give me my ratio, and it comes out to be 1.02. Yay, so it matches. So by doing a power of 2, I'm staying within 6%, worst case, of the ratio of the cost to the optimal costs.